Okay, so let's let's start talking about some applications. Okay, so one application that is hopefully familiar is this idea of motion. If you have time measured in seconds, position measured in meters is a function s of t. So s of t, this is for like linear motion. Okay, so an object moving back and forth along a line, or maybe up and down along a line. So position is s of t. Velocity is its first derivative, v of t, and acceleration is its second derivative, a of t. Now I put the units here: meters per second, and meters per second squared. So free fall motion in particular, free fall motion has some assumptions. Free fall motion assumes that the only force acting on the object is that of gravity. Okay. We're also going to assume for this application that we are, so that's first assumption. Second assumption is that we're close to the Earth. If we get far away from the Earth, then the model we're about to come up with would not be valid any longer. Third assumption would be, let's just take this formula we know, force equals mass times acceleration. This F equals ma is one of the basic formulas in like Newtonian physics, so we're going to take that. And so these assumptions together are going to give us a piece of information, which is that if the force is constant and the mass is constant, because we're close to the Earth and we're not moving fast enough for relativity to get involved, blah, 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 we're going to keep things simple here. Close to the Earth, the force of gravity is essentially constant, or close enough to constant. It's pulling in one direction, which is down towards the Earth, and we're going to assume the Earth is basically flat. We're going to treat it as if it's flat for purposes of this model. Then a constant force in a downwards direction with a constant mass is going to give us a constant acceleration. So, constant downward acceleration. And the value of that acceleration based on the force of gravity is negative, we're going to have a of t is negative 9.8 meters per second squared. Okay, so this is information that we're going to take as given. I'm not expecting you to be able to figure this out. This is just a fact based on how strong gravity is and how fast things fall. Okay, so that's our constant acceleration due to gravity. Now, if we take that idea, a of t equals negative 9.8, then we should be able to use this notion that acceleration is the derivative of velocity. We should be able to take that assumption and do a reverse, like a reverse derivative, an antiderivative. We're going to perform an integral to figure out what our velocity function is. So it's going to be the integral of our a of t dt. So this is the integral of negative 9.8 dt. Whoops. And the integral of negative 9.8 is going to be, since it's the integral of a constant, it's just going to be that number, negative 9.8, times t. Okay, and then plus a constant. Well, it turns out that the constant that you have here, you could put plus c and then figure out what that constant is. But it turns out that if t is 0, right, then all you have left over is that constant, because you're going to have negative 9.8 times 0. And so that constant is basically the initial velocity. So instead of writing plus c, I'm going to write plus v0. That constant value turns out to be the initial velocity. Okay, so there we go. So we got our velocity by doing an integral. This is a function for velocity. It's a linear function. Then the position can be found by doing an integral of velocity, right? Because velocity is the derivative of position. So we'll do an integral of velocity with respect to t. That'll be an integral of this function, negative 9.8t plus v0, with respect to t. So from that, we're going to have to use the power rule. We'll increase that t from t to the power 1 to t to the power 2. And then we'll divide by 2. So let's take the negative 9.8 and divide that by 2. That gives us negative 4.9. So we have negative 4.9 t squared. And then we'll have a plus v0 times t, because the integral of a constant is just itself times t. And then we'll get another plus constant on the end. This is an arbitrary constant, but it turns out that if t were equal to 0, these terms would both be 0, and that constant would be all that's left. So in this application, that constant you add has got to be the initial position, s of 0. And so we'll call that s0 like that. So, you've probably seen this, let me just write this again. You've probably seen this equation floating around. I mean, I think you saw it earlier this semester in our class, and if you've ever taken a physics class, even like a basic physics class, you've probably seen this. This is like the function that describes the motion of an object when you drop it or throw it in the air. This is the free fall motion equation. And where does it come from? It comes from the assumption that the force of gravity is constant. We're being close to the Earth, so that is going to be constant. The only force is gravity, close to the Earth, so gravity is constant. Mass is constant, therefore acceleration is constant, and then just do two integrals to get from acceleration back to velocity and then back to position. Okay, so this formula comes from the straight out of the rules for integration. Okay, so this is really cool. I really want to. I'm just going to take a minute to explain some things to you and maybe draw a picture. This means that if you know the acceleration of an object, you can just integrate twice to figure out the position of that object. As long as you know the initial velocity and the initial position, as long as you know those two pieces of information, then you can figure out a function to describe the object's position. Just via this information, this simple idea that you get from position to acceleration by taking derivatives. So we do antiderivatives to reverse that process. Okay, here's what's really cool. I'm getting excited. This is one of my favorite things. You know how much I love multivariable calculus, okay? So let's talk about that again for just a minute. In multivariable calculus, you learn how to describe like the motion of an object, in three-dimensional space, like x, y, z. You learn how to describe a path in three-dimensional space with what's called a vector function. So let's say that we're in space, right? And you have a rocket ship, and your rocket ship here is there we go. Is your rocket ship, and the rocket ship's going around, and it's following this path, right? And then the rocket ship gets to here, and this is now, okay? There's the rocket ship. Theoretically, you should know all of the forces acting on this ship, because if there's a moon over here, or if there's a sun over here, whatever is going on, like whatever objects there are around here in space, you should be able to calculate the force of gravity. Or if you're way, way deep out in space, you can assume there's no force of gravity. And if you're on the ship, then you know which direction you're firing your thruster in. So what you can do is you can say, okay, I'm firing my rockets in that direction, which means that I'm going to be actually having an acceleration, which is pointing that direction. You have an acceleration. Oops. You are in control of the acceleration, right? Because you are the one who are deciding which direction to point your rocket thrusters and how much to burn, right? So what force are you going to be exerting? You're in control of that. So that means that if you can describe your acceleration as a function of time, then you can, knowing your current position and your current velocity relative to something like the sun maybe, or the Earth if you're in orbit, you can then do the same exact idea of taking integrals to work backwards from acceleration to velocity and then velocity to position. And you can therefore predict what path your spaceship is going to take in the future. If anyone's ever played something like Kerbal Space Program, you might recall that you get to, if you essentially specify which direction you're going to fire your rocket thrusters in and how hard you're going to fire them, then you are determining your acceleration, and via calculus that determines your path, because it'll give you a position function. Okay, so that is all, there's really neat calculus going on under here, and it all has to do with integration or anti-differentiation. Okay, so yeah, when you get to multivariable calculus, you'll be able to literally do a problem like this on your homework, which is kind of exciting. For now, we're not going to be doing it in 3 dimensions, but we're basically doing something like this in 1 dimension. Okay. So yeah, I hope that's sort of exciting.